Yeah, they say the yes on the.
Oh, great.
Oh, okay. Well, that's a long time.
That's an old one.
All right, folks, we're going to get started with the next session. Can I just get people online to confirm that you can hear me loud and clear? Thank you.
Okay, that's good.
All right, our next speaker is Ramesh Bhatt. Please take it away.
Yeah, thanks. Okay, so good afternoon, everyone. So for those of you who don't know me, I'm Ramesh Bhatt. I'm from Curtin University, and I'm the science lead for pulsars and the fast transient science working group. Oh, what do I need? This won't work? No. Oh, sorry. Okay, so what do I do here?
Click in the middle.
Okay, really? Yeah, okay, now it's working. All right, so as a science working group, pulsars and fast transients is fairly new addition in the MWA collaboration, but as an activity, it has been there from day one of MWA operations. In fact, the very first science, pulsar science, first science publication to come out of a fully commissioned MWA was a pulsar publication on millisecond pulsar of 437. And that was using a prototype version of, or beta version of a voltage capture system. And then eventually the full voltage capture system was commissioned a couple of years from then. And that's what we call as like a legacy VCS. And that produced like a whole range of pulsar science and several PhDs and trained a lot of students. And in the process, we had to upgrade to MWAX, and that warranted quite a significant revamp in the software subsystems that was supporting the VCS functionality, and you will see why. And in around the same time, we also had started one of our major flagship projects, which is called Smart Survey, and an all-sky survey to do the sensitive searches for pulsars and fast transients in the entire southern sky. And as of last year, we have completed the data collection process for that project. And that's 4 petabytes of data in the CAN, all in the VCS mode, and it's going to be an excellent legacy data sets from the MWA, particularly in preparation for SKLO, Pulsar Science and Planning. So very broadly, pulsars and fast transients within the MWA context is the science that you can do with this VCS functionality and associated software subsystems and HPC pipelines. So that includes pulsars, which has been the dominant activity, but you can also use that capability for doing things like FRBs, GRBs, triggering on GW events, and other things like cosmic ray detection and passive radar applications. So the fundamental difference between the legacy VCS and the MWAX VCS is the signal path and where we tap our signal. So in the case of legacy VCS, we were getting our data after 2 stages of channelization, and that was like a 28 terabyte per hour kind of a data rate. And with the new VCS, MWAX, where the bit depth is larger and you have more tiles and more receivers, so that is significantly higher. And so that basically means that you have a very different data format, and you also have like a new pre-processing tools, as you have heard in the last 2 days of presentation. So that's what essentially warranted and a major redesign of the systems, which was pretty much like motivated by a lot of wisdom that we learned in the process. The whole idea there is to develop a system that can cater to both legacy VCS as well as the new VCS format, and do like a cater to multiple different science applications. And that effort was pretty much led by Sam McSweeney when he was part of the group, and that software is called the VCS Beam. And that's a very well documented and enormously user-friendly. And as of this point, that very first signal path, which is like a producing data for routine pulsar or FRB detections, which is something that we have put into routine production mode. And that was important because that is the only way we could have completed this smart survey project. Other things which can, in principle, possible, things like getting into higher time resolution for cosmic ray detection or doing offline correlation for fast imaging, all these bells and whistles are there. It can be enabled, but at the moment, the science push for that is not really high. So, but in principle, all that is possible. And if you are looking for details on what exactly we do in this subsystems, wait until Chris's talk, and he will give a quick rundown of various steps. Another important technical milestone is the migration to Cetonics. As you heard from both Dave and Greg yesterday, and we are very close to the end of life for Garawarla. And the only way to sustain and continue this activity forward is a seamless transition to Cetonics. In other words, pretty much having a hippified version of a VCS beam that can work on Cetonics. And as you can see, that's we had the first light on that as of a month ago. And left one is the Garawarla CUDA version of the VCS beam, and right one is the Cetonics. And as the details of these plots or numbers are irrelevant, but if you can see any difference in numbers or pixels, you can just shout. But basically, it's identical results, few minutes of crab pulsar observations from a few coarse channels. And this is a support, which is a project which is also supported by expert help from POSI, in particular, Christian D. Pietrantonio and Chris Harris helping Bradley Myers and Martin Sokolowski in moving forward in this effort. And of course, there are lots of things to do, like doing a more in-depth comparison and doing some detailed profiling and things like that. But the bottom line, just relaying some numbers from Bradley. So a significant part of that initial profiling seems to be IO, something like a half to almost 60%, and a quarter of that goes into like MPI communications overhead, and it's only a quarter that gets used for actual GPU processing and synchronization. Anyway, that was a quick summary of some important technical milestones. Now I will move on to more exciting science updates, and starting with the Smart Survey and Pulsar Science. And for those of you who don't know, and this is a very exciting and interesting project that nicely leverages some of the major strengths that MWA has to offer, which is a very large field of view, and the VCS subsystem, which allows you to do a high-time resolution sampling of a very large patch of the sky, and of course, compact configuration that brings us like enormous efficiency in the cost of beamforming. Those are basically the ingredients that led to the conception of this very ambitious survey. And the idea is to basically cover the entire southern sky in a very long dwell times. And the fact that, you can do like less than 100 hours, that's enormous efficiency in terms of data collection compared to all other telescopes, which have spent like thousands and thousands of hours and spreading this project over like several years. But that being said, that exchange in data collection is happily exchanged for like a pretty substantial cost in processing the data, particularly doing pulsar searching, and that's partly also because of we are working at low frequencies. In summary, that we have 4 petabytes of data in the scan. Every single observation is 40 to 80 terabytes of observation, and we are going to take a baby steps over the next 10 years or 5 years, and whatever the time scale it is going to take us. And at this point, we have completed what is called a first pass, which is like a shallow survey of some small parts of the sky. And in that process, we have completed the quality check for the entire data. And that alone has detected something like more than 200 non-pulsars, many of them for the first time at low frequencies, and a handful of new discoveries as well. And these discoveries are not just adding like a bunch of pulsar counts. It is much more than that. As you can see, that many of them are scientifically interesting on their own rise, and they all warranted like individual focused publications, some of them, in fact, more than one. And just to give you like a quick summary, this is going from clockwise, and the top left is our first pulsar. First pulsar is special because it's the first one, but it turns out to be like a steep spectrum, low luminosity class of objects. And that puts in like a rare lowermost 2% of the current non-pulsar population. And what is shown here is the MWA discovery observation, then detections from GMRT and the parks. And it's also located at a very high latitude and has a high variability. So a very promising object for probing the turbulence at a high latitude. And the one on the right is like a very fascinating object. It shows this sub-pulse drifting phenomenon. It's one of the most sought after phenomenon for chasing pulsar emission mechanism. Those tire track kind of patterns is essentially like a moving emission structure moving in pulse phase as the pulsar rotates. And that object has been quite an interesting one and fun to work with. Already we have had 2 publications focused on that particular one, and a 3rd student is currently engaged in follow-up of that project. 3rd one was kind of a vanilla pulsar, that's why it is not shown here. 4th one is yet another vanilla pulsar, but we had a lot of fun in localizing and getting its better position using GMRT, high resolution imaging, getting its right DM, and in the process, actually renaming the pulsar. So that was quite a fun exercise. And the most recent one, that's another subpulse drifter, but you are going to hear more about it from Garvit's presentations right after this. An important task that we need to do when we find a new pulsar candidate, we need to get its position within a few arc minutes kind of uncertainty. And that's very important to do regular targeted timing observations, because that is something that we need to do for every single object, because otherwise you can't claim that you have a new pulsar discovery. And of course, you need that better position to also go to other telescopes, particularly things like Parkes and GMRT, which operate at higher frequencies. So you need a better position. So initially, we used to use some sort of a likelihood approach, which sometimes works, sometimes doesn't work. And that sort of a situation sort of prompted us to develop this more robust and reliable, statistically rigorous approach for localizing, producing a localization map. And that's a work in progress by Bradley Myers and Arash Baramian. And this is their attempt to localize one of those most recently discovered pulsars. And as you can see that the relatively complex beam pattern of the compact has introduces some complexities here. And this is basically work in progress. It is motivated by localizing the smart pulsars, but in principle, it can also be used for localizing any other fast transients or even getting better positions of the currently known pulsars. Another important task that we have undertaken is a consolidation of all our calibration observations, which was particularly motivated by all these new pre-processing and calibration tools, which you heard a lot in the last 2 days, Birli and Hyperdrive. So the idea was to basically use these new calibration tools and produce calibration solutions for all our data sets and make them available on different places, including Data Central, so that anyone who wants to do this VCS-based science don't have to go through that painful exercise again. And that's already improving the efficiency for some of the papers that works, and particularly the data release papers that is currently in preparation. But again, it's mostly driven by like a smart needs, but it is also something which will come in enormously beneficial for a lot of non-smart science that will use VCS data. So in one of our description papers last year, we reported on an updated census from the first 4 campaigns, which is like a few years of data set collected for SMART. And that was already like 180 pulsars detected at low frequencies, which is shown in the summary plot, which is the red, orange, and green dots essentially. It's all MWA detections. And what is shown behind is like a gallery of profiles. And important thing is that, of course, we have increased the tally by another 30% by completion of the data set. This is going to be an enormously valuable data set, particularly for SKLO, pulsar survey, and science planning. The data sets are in the voltages, so that means you also have the options of reprocessing it in many different ways. They can be used for like a future algorithmic development purpose or uncovering new phenomena and so on. But most importantly, historically, every single major survey has benefited tremendously from the predecessor surveys, and multi-beam surveys is really a good example. And at the moment, there is no such reference survey for SKLO band. In fact, SMART is the first such a survey in the low frequencies in the southern sky. And it is going to be like a more sensitive than many of the previous generation surveys, particularly in the southern sky. So at the moment, we are working on a continuation of the SMART paper series, and both paper 3 and 4 are currently in preparation. And you will hear more about it from Chris's talk. And you can also use this data products for a whole bunch of science, and one of them is currently at works, and that is to look at pulse broadening measurements of a large sample of pulsars from MWA that is driven by the ongoing work to improve the electron density model for the galaxy. And this is the work in progress to develop the successor for NE 2001, which is an extensively used galactic electron density model. And this plot from Bradley nicely summarizes one of the things that I have been pitching for a long time, which is basically a paucity of useful measurements at high galactic latitudes. And that is exactly what we need to get better pulsar distances or doing more meaningful FRB interpretations. Again, another paper proposal has been circulated last week, and so as you can see that we are going to be incredibly busy. So in the meantime, we have been moving on to the transitioning to our second pass processing. The second pass processing is not just processing longer data sets, and we are also implementing like a multiple different kind of search algorithms, including fast folding algorithms, which has increased sensitivity to long period pulsars, and a better optimization of the type tessellating the sky, so we can improve the efficiency there. And also moving on to NT, which is the new version of upgraded version of 4-star. And of course, the migrating the whole, integrating the BCS beam into the search pipeline. So as you can see that it has been quite a significant effort. A lot of heavy lifting is done by TM in TAN. And just to give you some approximate numbers to give you the scale of the problem, for processing one smart observation, it turns out you are talking about 2,400 hours of time on a cluster of 24 GPUs and 31,000 CPU hours, and that's for just one observation. And that basically emphasizes the need to spread out this processing load, and that's why we are extremely keen to take on Stephen's offer and solutions to consider commercial computing solutions like that. So as you can see that at the moment we have processed 1/8 of the one observation, which is literally 0.2% of the sky, and we have our very first goodie. And at this point, it is worth explaining what these plots are. And the top left is like an integrated profile. Bottom one is signal strength versus time and phase. And the middle panel is the signal strength versus frequency and phase. And the rest of them are diagnostics and coming from the search routines showing signal strength in PP dot and DM space. Importantly, that you might want to look at these numbers, and you can see that this is a period which is much shorter than many of our earlier discoveries. And by looking at the period alone, you would say that, okay, it is another crab-like pulsar, which is itself is exciting. But the question that oftentimes pulsar people have to deal with, why someone didn't find it earlier? And Stephen sometimes like to ask this question, why Parks didn't find it earlier? I would rather ask the question, why we didn't find it earlier? So in case if it was not obvious to you, this is what a first pass search processing would have given to you. And with the second pass, which is a full observation processing, it is pretty unambiguous. And it's a pretty faint source. We are talking about an indicative flux density of few millijansky. And the nice thing about the smart survey is that every single patch of the sky is like covered at least twice. So instead of going back to Stephen straight away, we can go back to our own observations, smart observations, and do that confirmation observations. And in this case, it turns out just after a month, the period has changed. That will happily put that pulsar in somewhere which is very close to crab-like pulsar. But it turns out reality is something very different. In an observation that was taken almost 2 years ago, that was for Sammy's honors project, pulsar was detected, but with a period that is much shorter. So based on this small number of points, you would like to say that it's likely a part of a binary system because the period is short, potentially a partially recycled object, which makes it quite an exotic kind of an object. Unfortunately, we have not detected that at Parks, and it is way beyond the GMRT sky, which turns out good and bad. And the MWA follow-up is the only solution here, but we don't have the luxury of a beamformer. Otherwise, I would have probably told you what that object is like right now. So it's a follow-up is going to be a little bit slow and tedious kind of a process. And that's one of our big motivation to push for beamformer as a capability for MWA. So I just want to very quickly mention that there's a lot of interesting HPC and software challenges in the smart search pipeline. One of the most important one is, of course, the high cost of de-dispersion. There are potential solutions like Astro Accelerate, but that is heavily tuned for like, the SK emit, and that loses its efficiency for low frequencies. IO is like a very significant part of the cost here. And the most importantly, many of the downstream software we are using is pretty much like the software that was developed for single beam and single data streams. So there is a high level of efficiency that one can achieve here by developing fresh insights and identifying the bottlenecks and exploring the solutions. This is the work that we have started discussions with Emma Tolley and Piyush, and we hope to have some solutions for smart, but potentially, the idea is to make it more generic so that we can also offer that as a solution for SKLO or low frequency searches in general. So we have had quite a few publications, but you are going to hear more about it from Garvit's presentation. And Susmita's publication I will be covering in my transients update tomorrow. The other one which I want to quickly mention is a recent publication by Chris Lee from his honors work using a WAVS2. But MWA data was very useful as like a reference cross-check for validating that polarimetric exercise there. And some example profiles are shown here. But scientifically, there is a very interesting result where we see the evidence for microstructure in the magnetic field on a very short physical scales and a field reversal. To me, this is all like a very nice demonstration of the kind of exciting science that you can do once we have the luxury of MWA's beamformer. Of course, there has been quite a growing interest from researchers well outside, the MWA collaboration. Jim Cordes and his student Abra have been leading the work that's looking at the pulse broadening measurements and looking at the subtleties where pulse broadening functional form itself can develop a frequency dependence because of the strong dependence with the inner scale, and that's a very, very subtle effect. And they have an active project that is happening ongoing at MWA. And this is a smart observation of the same pulsar. I don't know why it is coming tilted. So you can imagine that, what it looks like. Jonah Rankin, who has been on the pulsar field from the day one of pulsar astronomy, has been very interested in this otherwise apparently abandoned pulsars. Nice and bright pulsars. From smart observation, we were able to produce this very nice looking pulsar. Pulse stack. But if you look at things like a longitude resolved fluctuation spectrum, which is a technique to look at the phase or amplitude modulation features, there is nothing super exciting. But according to Jonah, this is a very interesting pulsar to study the pulse profile evolution and apply special relativistic retardation aberration event effects, and you can deduce the emission heights. And that's again work in progress. That paper is coming very nicely because Jonah is writing it basically. Okay, so very quickly, how much time I have? 2 minutes. Okay, so some updates on the fast transients. This is the work that is led by Gemma Anderson and team. The idea here is to basically trigger the VCS and looking for prompt or persistent emission coming from GRBs. And there has been some very interesting result. And what is shown here is some tantalizing detections from one of the GRB triggers. This is about 6 to 7 sigma, nothing that will make you jump up the chair. And it also turns out that that band overlaps with the digital TV, and which can have some significant bandwidth. But assuming that there is a non-detection, if you turn that into like a fluence constraints, which is shown on the right plot, and at least this is for the model for like a GRB jet ISM interaction. In other words, jet impacting the ISM and producing an FRB-like emission. You can put some very interesting constraints. And this is the work that is led by Fan Shu. And again, a paper is at works. And another interesting work that they have been doing, the paper has been published, which is to like how to do the optimal triggering of gravitational wave events. And you can see from the sensitivity map on the top, there are 2 prime spots from LIGO, Virgo, Kagra combination. One of them is on the top of North America. The other one is in the Indian Ocean, not too far from where MWA is located. By splitting the telescope into 4 subarrays, you can optimally coverage the entire localization circle. And that is what is demonstrated from an example simulated GW event in the bottom panel. So finally, congratulations to our graduates, both Nick Swainson and Parul graduated earlier this year. And we have Brendan Hennessy and Susmita Seth, both approved to graduate. That is 4 PhD completions. And when my final point, which I have said before, I'm going to say it again. It has been a lot of fun working with the VCS data. We have learned a lot in the process, and that has enabled us to do this very exciting, ambitious, smart survey. But at the moment, there's a lot of exciting science that is knocking on the door, and that is something that we can make a big change, once we have a beamformer capability. I'll probably stop it there and leave the summary, and happy to take questions. Yes, there is a performance difference, but I mean, I'm not sure if Bradley is online, but there is definitely performance difference depending on which mode you are using. Say, for example, if you are generating, say, something like a PSR fits output, MPI overheads are like a lot higher compared to the other one. When I say like a performance difference is there, but they are like a consistent between the two, the numbers could be different. But within the VCS beam, if you try to run it in a different modes, you get like a different numbers for MPI communications overhead versus like a IO. IO seems to be like quite a significant difference between the different modes. But this is again, very initial numbers, I should say, something that came from, as a summary from Bradley as of yesterday, so maybe not the final ones. But the important thing that we are excited about is that we can reproduce the identical detection. That's the important part, right? Like I said, we have another 4 more months to converge on this, and before Garawala is no longer available, but it's in the right direction. Yes, Stephen.
It's probably worth pointing out that the smart archive of voltages records the entire information state of the electric field forever. So that's a resource not just for high resolution science, but you can correlate those data, you can reproduce any MWA data products you desire from those voltages and do any MWA experiment. I mean, accepting the fact that 8 at 12 time. So that's an enormously unique and powerful data set for posterity. So probably before 2030, we should do it all again and record the sky again. Longer than 80 minutes.
Yeah, I can't agree with you more. This is fantastic. See, I've been telling this to Greg and others. The smart data set, like you said, is very excellent data sets. But we should keep in mind that all of that was taken using compact configuration. So for doing things like imaging pulsar sensors or localization or doing a combination of imaging and other types of science, that may not be the most useful data set. So I have been advocating that as a important legacy data sets from MWA could be like one data set that is using the smart one, which is great for like a time domain pulsar searching. And like you said, either using 256 or long baseline, we have like one full legacy data set for the entire sky. That combination will be like a fantastic. In fact, some of that can also like expedite the discovery and characterization of the pulsars, because when you find a pulsar candidate, one of the biggest challenges is that locating that pulsar where in the sky. That is where long baseline configurations, which much more comfortable beam pattern, can be like incredibly useful.
Maybe a comment on the question before. So Bradley Mayer answer.
Yeah.
You may.
Okay. So this is answer to Greg's question. As Ramesh says, the dominating factor is IO, and the split changes depend on which output mode. Nothing different from what I have said. That's good. So at least I was not misrepresenting anything that I read in a quick email. Yes, Greg. Yeah.
But I think it's key to say that the other 2 years smart survey where we haven't got funding for the reverse stuff, it probably doesn't actually matter. We will obviously be punching the smart.
Yeah.
Hanging fruit and late. The second thing I was just going to ask is at what point in the process, like how early in the process, do you realize that the data quality requires reserve, or will you only know that at the end of processing an entire field?
We do that straight away. So as soon as Andrew has completed the observation, as soon as it gets to the disk, we just pick up like a 10 minutes of data, do all our calibration, do our quality check. And if we are not satisfied with through our sanity check, like, that non-pulsar detections, we just basically request a rescheduling. So every single smart observation that goes into the archive is the one that has been properly quality checked. There have been occasions in the past when, some observations have to be done twice, thrice, or even 4 times, as the extreme case. But during the Nick Swainson times or now Chris Lee, when the campaign is on, this is what we do, just have like a dedicated resource who can jump onto the data. So that is the reason why we have the pulsars throughout the sky. so 230 pulsars. So it's all nicely quality checked. Yes.
One more round of applause for Ramesh, thanks. Thanks, Ramesh. All right, now we have Garvit Grover with the implications of quasi-periodically nulling on the pulsar death mechanism. Take it away, Garvit.
Can I be heard?
You certainly are.
So yep, that's my talk. Real quick, I'll just give some few definitions to get everyone acquainted to what I'm going to be talking about. So nulling is this phenomenon we see in pulsars where instead of expecting them to be on all the time, they turn off temporarily. And this temporary cessation you can see in different varieties, in different pulsars. And normally we see as stochastic. So as you can see on the figure on the right, the pulsar turning on and off, and that can happen in different ways. Typically, how you would report or analyze this nulling is reporting two parameters, the nulling fraction, so fraction of the time the pulsar nulls, and the nulling duration, so the average duration of each nulling sequence. For subpulse drifting, because it's kind of relevant but not the main focus. So normally pulsars, we see them stay at one pulse phase throughout time. So on this plot here, if the pulsar was not subpulse drifting, it would make a straight line. However, pulsars tend to, that show subpulse drifting, they change their pulse phase throughout time, and this can leave this tire track shape here. And this is not a real example. Pulsars do tend to behave like this sometimes, but in some cases, pulsars also can be very misbehaved. But that's a topic for another talk. So yes, pulsars. So this on the plot on the right hand side here is a PP dot diagram. It's a period of a pulsar against the period derivative. Typically, you see pulsars on the top left hand side of here when they're younger, and as they age, the period increases and their P dot decreases, and they end up on this side of the plot. And as you can see, there's a large vacuum here of pulsar detections, and that's because we don't really see them there. And we think that pulsars don't emit radiation at the parameter ranges, and hence they're considered dead. To theorize where pulsars could possibly die, people have made these limits called death lines. And because people have very different assumptions of what a pulsar could be behaving like, or what the emission mechanism could be, there is a variety of death lines. I've only plotted 4 here. And this region we call the death valley because there could be different types of pulsars that die at different ranges. As you can see, these death line or constraints aren't that great because you see a whole bunch of pulsars leaking outside of that range. So we don't quite constraining our limit should be yet, but that's ongoing work. And you'll notice here in red are all pulsars that show nulling. Now, early days of nulling, when people started figuring out, there actually was some patterns people noticed that there was some correlation with the pulsar's nulling fraction and the period of a pulsar, and even the age of the pulsar. So people expected that as pulsars age, they null more and more. And that's a very common connection to make with pulsars aging and dying, because as it's nulling, it's emitting less and less pulses until it just turns off one day. But as we have a whole bunch of pulsars we've detected to show nulling, when you fill this parameter range, you can't really see any sort of correlation. And there's been studies to show that there is no conclusive evidence that there is a correlation between nulling and other pulsar parameters. Now, in this plot, you can see there's a nice little star, and that star is the pulsar MWA in the Smart Survey. So this pulsar is a very typical boring pulsar, middle-aged. It's got a period of about 1.66 seconds, which is slightly longer than average. Looks pretty boring, except when you start looking at this pulsar more in single pulse data. You can see on the two right-hand side panels, this is the single pulse data for the pulsar. And the most right-hand side panel is the zoomed version of the middle panel. And straight away, you can see that the pulsar does show nulling, and it does show subpulse drifting. Now, what's really interesting about the pulsar, you may just be able to see it visually, that the nulling seems to be somewhat periodic here. So typically with nulling, we think it's stochastic. It's almost pseudo-random, but there hasn't been really much study showing many pulsars showing quasi-periodic nulling. So we tried to delve further into this and had 3 observations. So like Ramesh mentioned, each patch on the sky gets covered at least twice. Luckily for this pulsar, it was covered 3 times with 3 different observations. So we had 3 different data sets to look at. And for each data set, I simply did a FFT on the pulse intensities over time. And in each 3 observations, you can see that spike in the low frequency part of the spectrum, and a low frequency period, which in this case is called nulling. And when you average it, you get a density of about 42 pulses. Now, this work that we've done is already been published in this paper, and you can see it here. And obviously, since we found this one, we also were interested in other pulsars that are quasi-periodic nulling. So in the same paper, look as to what other quasi-periodic nulling pulsars there are. There actually aren't that many. There's about 1% of the pulsar population shows this behavior, which isn't a lot. And so from these papers, I managed to collect whatever people thought they knew of quasi-periodic nulling pulsars there were in the population. Now, straight away, you can see they tend to be in this middle patch here, and interestingly, they are in this Death Valley region, or the Death Line region, which is pretty interesting. Now, as to the interpretations of this, so past models, such as the carousel model, which is very popular in trying to explain subpulse drifting, that model also describes this behavior is possible, the quasi-periodic nulling behavior. If you can imagine on the sky of on the pole of the pulsar, there is a carousel of beams that are emitting, and each time one of us crosses our line of sight, which causes the drifting behavior that we see. And if you can imagine, every second one, for example, is turned off, that could, for example, show you some quasi-periodic nulling in your observations. And this could be an explanation as to how that happened. Sadly, from what we've seen, not all pulsars that show quasi-periodic nulling show subpulse drifting. So you can't say this is a very solid explanation for why we see that. And as to new models that try to explain this, there has been theoretical models about axions, light axions, causing nulling in the pulsar atmosphere. There's also been a nice, interesting paper about interpreting a pulsar as a RLC circuit, and it's almost like a capacitor releasing energy and it having to charge up. And somehow, well, they're actually pretty interesting, but they are all theoretical so far, and they don't have a real comparison to actual pulsar applications. So now onto our interpretations. So if you can look at the trend here, they seem to be almost in line with the trend or the gradient of the death lines that we have. And now these
warning.
Yeah. So these death lines are based on the period and the magnetic field, or the P dot in this case. They can be interchanged. But the interpretation could be that whatever mechanism is causing there to be quasi-periodic nulling specifically is related to the some magnetic change in the pulsar's magnetic sphere that could be causing this. However, this a bunch of examples that we have is from few papers that have each measured this behavior in their own different way. So you can't really conclusively say yet that this is exactly how things are unless one person does it consistently for all of them. In fact, I also found this paper that's fairly old, from 2007, that actually also measured a fair few of nulling periodicity. It just called it something different, those people never picked it up. And so when I actually add that into this data set, you can see on the right hand side here, it fill up this middle space more. But you can also see it also fills up this left hand side space as well. Now this paper, what it does is it does average over a whole bunch of data to try and get good measurements. It is slightly less reliable because each pulsar here is being measured a different way. So our attempt in the future is going to be to try and do all of this consistently and see if there is a good correlation between the nulling periodicity and maybe the pulsar age or even the period. First, we will find more long period pulsars in that range that we can try and look for this nulling and sub-quasiperiodic behavior. However, when you look in this parameter range, there's typically some issues you have because the sensitivity for these pulsars is not that good. You have red noise coming in the way, which disrupts or lowers your sensitivity. Short observations are typically preferred, especially in the past, for pulsar observations. And since pulsars in this range are going to be a long period, you're not really going to be that sensitive. And past algorithms that were used for pulsars, even now, they're both all FFT based. And FFTs have been shown to be less sensitive to that parameter range. So in the future, and even now, luckily you've been seeing more surveys such as Smart Survey that have long duration observations, which make them more sensitive for this parameter range. And there are alternate algorithms that have been used to try and find long period pulsars and even nulling pulsars in that range. This include the fast folding algorithm and single pulse search, which have both been shown to be very sensitive in that parameter range. Now, lucky for us, or well, luckily, I also did a study on this to try and interpret and make a simulation of how pulsars in this parameter range will be detected using these FFT fast folding algorithm and single pulse search methods, and how future surveys could be benefit from looking at these pulsars in this way. So have a look at that if you like. But now what I'm focusing on is using the pulsars that we've detected with the MWA and Smart Survey to try and characterize nulling in a more detailed way that previously has been done using the pulse energy, the pulse width, and the signal to noise. And using that detailed analysis, we can then characterize these key values such as the nulling fraction, the nulling duration, the quasi-periodicity, all of that. And hopefully we can find some sort of answer to this correlation that's always been there with nulling and pulsar death. And that is all. I'll leave you with my slide. Thank you.
Thanks, Garvit. Sorry, I was on mute for everyone clapping in the room, so you wouldn't have heard it. Does anyone have any questions? Nothing in the room. How about on the chat? Nope. All right. Sounds like that was very clearly explained. So our next speaker is Marcin Sokolowski, who's going to be talking about high time resolution GPU imager for FRB searches at low radio frequencies. So we'll just set up the PowerPoint. Where is it? That second one, I think. It'll be the second one. Yep. There's your mic.
The arrow. Okay.
Perfect.
Okay, thanks very much, Dev. Can everyone hear me, see me, and so on? Okay, cool. Yeah, so today my name is Marcin Sokołowski, and I work at ICRA Keltin University in Perth, and today I'm going to talk about the high-time resolution imager using graphical processing units, GPUs, that we developed to process high-time resolution data, mainly the data from the MWA, so MWA voltage data which Ramesh was talking about, and use this high-time resolution images to look for fast radio bells or FRBs. So this work has been done in collaboration with POSI Supercomputer Center in Perth and OSSRC, and from POSI, Christian Di Pietrantonio, who is my PhD student, is doing currently bulk of the work. And we also collaborate with our former colleagues from Keltin, currently at SKAO, Danny Price and Randall White. So, yeah, that's just moving. Thank you. Okay, so just briefly, FRBs, probably everybody knows what they are, very short millisecond duration radio pulses, discovered just 15 years ago by Lorimer et al. In archive data from Muriyang or Parkes radio telescope in Australia. They can be highly dispersed, so that means that the radio pulse arrives earlier at higher frequency and later at low frequency, and the delay is given by the equation at the bottom. So they are very bright, involve coherent emission mechanisms, and they can be energies emitted in radio can be of the order of even 10 to 40 ergs. Some of them repeat, and they were observed from very high frequencies of the order of few gigahertz down to even 100 megahertz, but very few were observed at these very low frequencies and at MWA-like frequencies. That's maybe physical reason. There may be physical reasons for this, such as absorption at the source in the local environment, or pulse broadening due to scattering, so propagation effects. However, as chime data indicates, many of them, like in the panel on the left, you see dynamic spectra from chime. And if you see, take random collection, above half of them have very bright pulses reaching frequencies of 400 megahertz. So there is no reason that we can't see signal. There are no signals below this frequency, and we should really see more of this FRBs at frequencies below 300 megahertz as well. So, and similarly, this so-called galactic FRB from soft gamma repeater 1935 was also observed by chime down to 400 megahertz, and it was extremely bright with the order of hundreds of Jansky kilo-Jansky milliseconds. So we should expect that, and in fact, some FRBs were observed at very low frequencies. So this particular repeating FRB was detected by LOFAR down to 100 megahertz frequency. However, this is, well, that's good, but there is only few of those cases, and this is a repeating FRB. So in this case, we know exactly where to point our telescope, and we need to look there sufficiently long to detect one. So if we want to find, blindly look for this FRBs or in non-targeted searches, we have to analyze a lot of data from the larger patches of sky, and the main problem here at low frequencies is computational challenges, because if you consider FRB of DM of the order of 1,000 parsecs per centimeter cube, then this dispersive delay time for such an FRB at 230 megahertz is about 25 seconds, which means that if you want to look at the data in 110 millisecond time resolution over 300 channels, and you want to analyze 200 by 200 pixel patch of the sky, you need to keep about 1 terabyte of memory, data in memory, to be able to look back into this over this whole dispersed time, over this whole 25 seconds. So if we relax this requirement a bit and go to a lower time resolution of 100 milliseconds, it goes down to this memory requirement is slightly more manageable, of the order of 10 gigabytes. But in any case, we have to push this amount of memory through our systems. So this also requires large memory bandwidths of the order of hundreds of gigabytes. So, however, this fortunately was handled by the gamers, and they were pushing the limits for this, because if you want to have high time resolution videos, 5,000 by 5,000 pixels, 100 frames per second, it's order of at least 10 gigabytes a second memory bandwidth too. So previous FRB searches, non-targeted searches, there were a couple of them. Selective list here, apologies, not everyone is here. But with MWA, Stephen did his survey a few years ago, half day of data analyzed, and unfortunately no FRB found, but 1 year of such process of data process, if they would have processed 1 year of data, expectation is that they would detect about a few FRBs. So Ian Kemp, Stephen's student, recently upgraded the search with a bit more data, and it's going in good direction because he apparently observed a bit larger patch of the sky and more data. And so if we continue going in this direction, processing more data, we should finally detect first FRBs with MWA. I would like to make a point that I really like the idea of using actually all-sky imaging capabilities of SKLO stations, which can form images of the entire sky. So, and push our detection rate by increasing field of view to some 12,000 square degrees, which with reasonable sensitivity of the order of 200 Jansky millisecond can yield even hundreds of FRBs per year. So that's something that we can do. So now, how to handle these computational challenges? So there are two ways of, like traditionally FRBs were searched in beamformed data. So in this case, you can think about it, just single dish detects detects voltages, forms time series of these voltages, Fourier transform them, forms dynamic spectrum, and searches for this dispersed pulses. So in this case, we need to add this voltage, like if we have interferometers like MWA, we have multiple antennas, and we record these voltages from all the antennas, tiles in this case, like in MWA VCS data, we need to work in full-time resolution. So computational complexity is of the order of total number of pixels times number of antennas, because we have to add these voltages from all these antennas. And if we look at imaging, the computational cost is dominated by correlation, which has to happen in full-time resolution. So this is given by this equation. And then once we have visibilities and we put them on UV plane and grid them, we already average this visibilities in time. So the computational complexity is also of the order of number of antennas squared, but in this case is lower by the averaging factor. And similarly, imaging, in this case, it's two-dimensional FFT, so number of pixels times log number of pixels, but also data rate here is lower by the averaging ratio. So if we take ratio of these computational costs, it is given by this equation, and you may see or may not see that for some parameter range, this ratio is actually much greater than 1. So beamforming is computationally more expensive than imaging, especially for large number of antennas or pixels. It can be even a few orders of magnitude more computationally expensive. So that's why we are going for imaging. And additionally, we want to use the GPUs. So obviously, they've been around for a while. If you ever played Quake, you know that they are very useful. I haven't played much recently. I am writing my own game to find FRBs. This is kind of another, yeah, it has some complications. They are quite powerful these days. And if you look at the most modern GPUs like NVIDIA A100 or counterpart AMD MI250, they both have computing power of the order of tens of teraflops in 4-byte precision, or memory of the order of 100 gigabytes, memory bandwidth even of order of few terabytes a second. So they are sufficiently powerful to help us with this. And especially a lot of supercomputer centers these days actually starts to use them as their main horsepower. So new Setonic supercomputer in Perth, which is now POSI bought it as upgrade of their infrastructure. It has about order of 200,000 CPU cores and similar number of GPU cores. And they are, in this case, they are AMD GPUs, so MI250X GPUs. And because the code is slightly different for these GPUs than for NVIDIA GPUs, POSI initiated projects, software projects to help them transition various software projects to this new architecture. And well, in our case, we didn't have software. We wrote this imager software from scratch, actually. So just briefly, a little bit of code in here. So if you, we wrote like NVIDIA uses CUDA framework and AMD uses HIP framework, and Ramesh already mentioned this. So the structure of the code is very similar, just instead of having functions like CUDA malloc, we have HIP malloc, CUDA memcopy, HIP memcopy, etc. You can, in principle, compile this HIP code on NVIDIA as well, but that requires this HIP framework to be present. So we actually develop this GPU macros. So we have GPU malloc or GPU memcopy or GPU FFT, etc., which expand to CUDA functions or HIP functions based on what compiler is being used. So this is kind of what we are using. And now, so now to the imager itself. So we start with visibilities, correlation matrix. We apply complex, of course, so that's why 2 images. And we apply corrections and calibration. We put these visibilities on UV grid. We then two-dimensional Fourier transform, and this is example of the image from EDA2, SKA prototype station EDA2. So this is all sky image. Here you can see galactic plane and sun, not the best image, but that's just delta image from this imager. And imaginary part have to be 0, which is basically our diagnostic. If it's not, then something is wrong. So we tested this imager first on EDA2 data. On the right, you can see image from our imager. On the left, well-established imager, Myriad, CASA. So they basically look the same. Simulated EDA2 data, again, our imager against Myriad. Also MWA data, in this case, simulated the visibilities from Hydra A. Blink is our imager versus WS clean image. And if you compare this GPU version of two-dimensional FFT to CPU version, you can see that execution time as number of images is here. It's actually about 3 orders of magnitude faster using QFFT than CPU FFT, and similarly in gridding. In this case, also few orders of magnitude faster on GPU than on CPU. Now, Christian Di Pietrantonio, PhD student, is currently working to incorporate this imager into a fully GPU-based pipeline, which will basically read these complex voltages from the archive or from the telescope and therefore load them to GPU memory. We'll never leave GPU memory, hopefully. We don't want any additional I/O operations or moving data between GPU and CPU memory. So correlation will be done on GPU, applying all corrections and calibration, gridding, imaging, and then forming dynamic spectra and looking for FRBs will all happen on GPU. So this is work in progress. We haven't got dynamic spectra yet, but I can show you the image from MWA VCS data. This is 1 second of data processed with this pipeline. So everything was done on GPU, starting from voltage capture voltages. And this is our image. This is WS clean image, basically kind of the same. They are both delta images, the same sources. Well, if you look carefully, you will find bugs like this aliased source here, because we still have some aliased sources because we don't do the convolution, and or either we can do image of the entire sky to avoid ghost sources like this, but that will be solved soon. So we can currently image 1 second images or higher time resolution. Christian is currently working on doing all many fine channels, and the next step, well, then we can talk about doing dynamic spectrum and looking for FRBs with this. So last thing that I want to briefly mention is that I would also like to use this imager for to do high time resolution imaging with EDA2 station or other SK low stations because they are great for all sky imaging. I did some first kind of pilot transient searches with these all sky images in 2-second time resolution using just 1 megahertz worth of bandwidth. Not great, but we could still find some astrophysical transients due to known pulsars like B0950 using difference imaging. So there are 2 images and difference between them on the right. So this was published a few years ago. Now, the next step would be to increase the observing bandwidth and go to higher time resolution. And if we can do this, we can get up to limiting fluence of the order of 200, 300 Jansky millisecond, 10 millisecond or 100 millisecond time resolution. We can get to the point where we can be at a sensitivity where we could potentially detect 1 FRB per day. So that would be good. So if we can get there, so I'm working on this other thing, like how to increase this observing bandwidth and go to this higher time resolution. And then this is some kind of pilot survey that I performed using just 1 megahertz worth of bandwidth, 32 fine channels at 230 megahertz. So obviously this is not enough bandwidth to detect FRBs, and we would have to observe for longer. This is in 100 millisecond time resolution. Once we have this kind of images, this was done with this imager that I showed, then we have to look at every single direction in the sky, build a dynamic spectrum and look for dispersed pulses. In this case, we only detect non-dispersed pulses. These vertical lines are basically most likely due to RFI. If we go back to images, we see that there is probably some satellite emitting RFI, not what we are looking for. And yeah, okay, I got to the end. So just would like to stress 2 points that this imager has now been published. It's available on GitHub, and pipeline is being in preparation. Hopefully will also be published soon. And yeah, we want to use it on MWA VCS data, but also probably on all sky data from SKA stations. And I don't see any reason why it couldn't be also used to image standard MWA visibilities and do real-time imaging. And I think even if I don't see straight away science case for this, I think something cool would come out of this. And the other thing is that potentially we could insert into this pipeline some more modern imaging techniques like EPIC imaging or something that Emma here is working. So I would be happy to talk about it as well during this meeting. And yeah, okay, that's it.
Thank you, Michael. Any questions?
So you mentioned that you have plans to use VCS data, and I remember that Christian and you were also thinking about doing it on smart database. But in terms of the computational thing, how do the things scale up? Are there any showstoppers?
Well, because at this point we are still we were still testing the pipeline and doing like 1 second images, not 10 or 100. I can't tell you how the processing will go, but I think there shouldn't be any showstoppers really to do this. And I mean, this is the plan, Christian's plan. Actually, this is planned for the second paper. First paper is just to have a pipeline which actually does the job. And then benchmarking will be part of this paper. I can't tell you the benchmarks now, but the plan for the next paper and work is to actually process at least initially one smart observation, and then hopefully more, and maybe entire archive in this high time resolution mode and find something, hopefully.
We're ahead of time, so we've got plenty of time for questions.
Ahead of time, I could speak longer.
No. Garvit went under, so.
No, there's the question.
Great.
Just a comment, actually. So having a real-time image of the sky coming out of the MWA, even if it is, or even if it's near real-time, would be super useful for diagnostics or the wow factor of,
Public. Yeah.
So what's the MWA looking at right now?
Yeah, well, I totally agree. That's what I was hoping we could do. I mean, there are a few coding steps here, like read the use MWA lib to read visibility straight away without, you know, converting to any CASA. We don't like these conversions and IO. So yeah, but
How about online?
No question from online. Okay. No.
Maybe we'll just pass them online. Anyone online have any questions? If not, then we'll thank Marcin again. And then we will just get set up for Christopher Lee, who'll be talking about a census of millisecond pulsars with the MWA. So we're just setting up. Do we have anything else we need to do? We just need to stop sharing, right? There we go. All right, Christopher, take it away. Christopher, if you're speaking, we can't hear you yet.
All right, so I'm going to be talking
Thanks.
about a census of millisecond pulsars with the MWA. So I'd first like to acknowledge my supervisors, Ramesh, Bradley, and Willem. So what are millisecond pulsars? So pulsars are born fast, but they pretty quickly lose energy due to emission of magnetic dipole radiation. And during this initial spin down phase, we call them normal pulsars, and most of them have spin periods of about 1 second, and they spin down at a rate of about 10 nanoseconds per year. But a lot of pulsars are actually in binary systems with lower mass companions that evolve later on, and when they evolve, they begin to transfer mass onto the pulsar, and that causes a spin up of the pulsar due to conservation of angular momentum. And it forms what we call a millisecond pulsar, which spins at a rate of about 1 millisecond, and it spins down at a rate of only about 1 picosecond per year. And that's because millisecond pulsars have much weaker magnetic fields, and that causes them to have much less magnetic braking from emission of dipole radiation. So what we have at the end is a very fast pulsar that spins down very slowly. And millisecond pulsars are the most precise clocks, natural clocks in the known universe. So just to give you an idea of how precise they are, so the pulse arrival times can pretty easily be measured to less than 1% of the spin period of the pulsar. And a typical millisecond pulsar will rotate like 10 to the 10 times per year. So that gives us a precision of about 10 to the minus 12 milliseconds after about 1 year of timing the pulsar. So what can we do with such a high precision? Well, millisecond pulsars are one of the best ways to probe general relativity. So you can do it in, I guess, one of two ways, or either of two ways. You can either time a millisecond pulsar, which is in a binary system, and you can very precisely measure the orbital parameters and the relativistic orbital parameters of the system. So on this slide, I'm showing the orbital decay of the double pulsar due to emission of gravitational waves. So this is a paper by Kramer et al. 2021. And the red line in this plot is the prediction from general relativity, and the blue dots are the measurements from pulsar timing. So this just shows the precision which we're able to use millisecond pulsars to test general relativity. And the other way is, of course, pulsar timing arrays. So if you have a collection of millisecond pulsars, you can use them to search for low frequency gravitational waves. So ever since millisecond pulsars were first discovered, there's been questions around whether there's any fundamental differences in their emission properties compared to normal pulsars, because they're both at different stages of their evolutionary cycle, and this could, of course, potentially cause changes in their emission properties. So one way that we can test this is by using observations over a really broad frequency range, because we can measure things like the pulse profile evolution, the pulse width, and the flux density spectra. So just to give you an example, the intrinsic profile width of millisecond pulsars scales a lot more slowly with frequency compared to normal pulsars. And there's been speculation that this is related to the fact that millisecond pulsars have much more compact magnetospheres. So this just shows that having observations over a large frequency range can help us to better understand the emission mechanism. And one of the examples I'm showing here on the screen is from a census of millisecond pulsars with the LOFAR telescope, which was done a few years ago, which really helped to contribute to our understanding of how the profiles change with frequency. So just getting back to how we actually collect high time resolution data with the MWA. So of course we start with the VCS system. It records 10 kilohertz channelized voltages. And then we coherently beamform those voltages towards anywhere in the primary beam. And then depending on the scientific application, we either detect those voltages and then save them as Stokes parameters at the 10 kilohertz frequency resolution / 100 microsecond time resolution. So this is what we do for all the regular pulsar searching. Or for more high time resolution applications like observing millisecond pulsars, what we do is we put it through an additional step, which is the polyphase synthesis filter, which recovers the 1.28 megahertz coarse channels, which have a much higher time resolution of 0.78 microseconds. So this is what we do for all of the millisecond pulsar observations. And this output stage also, we save it as complex voltages, which allows us to coherently dedisperse the signal. So this basically completely removes the effects of dispersion from the interstellar medium, which helps to recover the detail in the millisecond pulsar profiles. So for this work, we make use of the SMART survey, which Ramesh already talked about. So it's a survey of the entire southern sky using the VCS system. We tessellate the sky in 71 pointings, and it's centered, it covers 140 to 170 megahertz. So this is a very useful resource for us, and it means that we don't need to go out and collect any more additional observations to actually observe all of the millisecond pulsars that we want to observe. So the MWA has, of course, already established itself as a very useful instrument for high time. So an example that I'm giving here is that we've done studies of 0437 and 2241, which are two very high profile and useful pulsars for pulsar timing arrays because they're some of the brightest pulsars in the sky. And observations of the MWA have contributed to our understanding of how their profiles evolve with frequency. And that is, of course, useful for getting the most precise times of arrivals of these pulses. And we also measure things like dispersion measure, which we're most sensitive to at low frequencies. But although we've already done a lot of studies of millisecond pulsars, we haven't yet actually done a full census of millisecond pulsars. And now that the SMART survey data collection has been completed, it enables us to essentially go ahead and actually perform a full census. So this census will be complementary to the Northern Sky census, which was performed by LOFAR. And it will give us a much more complete picture of the MSP population below 200 megahertz, because of course we cover a lot of the galactic plane in the southern hemisphere, which is where a lot of the pulsars lie. So the plan in this project is to observe about 110 millisecond pulsars, which would cover the vast majority that we're able to detect with the MWA. So one of the things that we need to consider is how we maximize the sensitivity of the census whilst minimizing the computational cost, or at least minimizing the amount of data that we have to download and process because the observations are so large. And one of the challenges that we have to deal with is that the observations are, of course, drift scans. So if I wanted to download just a 20-minute segment of an observation, then that might be really good for one pulsar, which is at the peak of the beam power, but another pulsar might already be leaving the beam at that point of the observation. So I need to be, I guess, careful with choosing the portion of the observation that I download so that we can have full sensitivity towards all of the MSPs that we're targeting, whilst not downloading the entire survey, which is, of course, a lot of data. So I decided to just download the best 30 minutes of each MSP. So that means that for each of the observations that we selected, we downloaded between 30 and 80 minutes of data. And in the end, we only need to download about 35% of the SMART survey to actually observe all of these 110 targets for at least 30 minutes. So between 30 and 80 minutes. So this is, I guess, a summary of the census. So we've detected 31 MSPs so far, with 31 yet to observe. 48 were non-detections, and a lot of the non-detections lie along the galactic plane, where, of course, dispersion and the effects of scattering are much higher. As you can see, most of the observations that we ended up downloading are along the galactic plane, because that is where most of the millisecond pulsars are lying. So this is some parameter distributions of the pulsars that we've observed and detected. So on the left is a PP dot diagram. So we've detected MSPs all the way down to less than 2 milliseconds in period, and all the way up to just the partially recycled MSPs, which have periods of like 20 to 30 milliseconds. So we have a sort of a good sampling of the whole millisecond pulsar population distribution in the PP dot diagram. And then on the right, I've put a plot together of DM versus galactic latitude. So we're sampling a wide range of galactic latitudes. And then DM you can think of as a proxy for distance. So this is basically how far or how deep we are detecting pulsars into the galactic plane. And we're detecting DMs up to about 60 or 70. And then beyond that, a lot of these MSPs are too scattered for us to detect. So this is a subset of detections from the census so far. So there's, I guess, a range of signal to noise that we're seeing here. But for some of these more bright millisecond pulsars, like 0437 and 2145, we're able to do a much more in-depth analysis beyond just like flux density measurements and profile width measurements. We can also do polarimetry. So what I'm showing here is a full polarization profile of 2145. And we've been looking at the spin phase dependence of rotation measure. So Faraday rotation is a frequency dependent rotation of the polarization vector, which is caused by the signals propagating through a birefringent medium, like the magneto-ionized interstellar medium. So we've taken measurements of RM as a function of the pulse rotation phase. And since the RM is varying, this must essentially be originating from the pulsar's magnetosphere, which is a contribution to the rotation measure, which is not normally studied. And in particular, it's not usually studied for low DM pulsars. There's been some studies of this for much higher DM pulsars, like the Vela pulsar. So this is a pretty interesting result that we've been able to obtain, and we're going to be investigating this for a few more of the bright millisecond pulsars that we've been able to detect. And of course, this particular type of study is particularly powerful at low frequencies because we have the sensitivity to measure rotation measure with such high precision. So another way that we can sort of gain an understanding of the emission mechanism is by looking at the flux density spectra. So the spectral indices of normal pulsars and millisecond pulsars are typically follow the same distribution, so they're pretty much indistinguishable based on a lot of recent studies. But it has been pretty widely reported that millisecond pulsar spectra are much more simple in that they don't really show any signs of low frequency turnovers. And the select few that do show hints of turnovers indicate that they have turnovers at much lower frequencies, sort of below 100 megahertz, which is a sort of interesting discrepancy between observations of MSPs and normal pulsars. So to sort of further investigate this, we'll be measuring flux densities in the SMART survey, which will be contributing towards the lower end of the flux density spectra, and then modeling the spectra using our program Pulsar Spectra, which includes a comprehensive flux density catalog compiled from the literature. And it's been updated with bandwidth integration and a full Bayesian nested sampling analysis so that we can sort of get a better understanding of the significance of the model fit and the uncertainties in the fit. So we'll be applying this to all of the pulsars that we're able to obtain flux density measurements for. So the next steps for us after the census will be to do a targeted search, because of course a full blind search for millisecond or binary pulsars in the SMART survey is really computationally infeasible because it introduces additional search parameters. In particular, the acceleration search is an entire other dimension that we would have to search. So what we do is we are going to target unassociated Fermi gamma ray sources. So we've built a targeted search pipeline that makes use of a semi-coherent dedispersion strategy, which will help us to maintain sensitivity up to a much higher dispersion measure, which is particularly important for millisecond pulsars because the intrachannel dispersion smearing is particularly disruptive for, or it particularly degrades the signals of millisecond pulsars because the spin period is much shorter. And the MSP sensors will actually help us to inform this search because it will help us to choose the DM range and also the orbital period search range and the optimal integration length. So it will sort of give us a better understanding of the population that we're able to observe with the MWA and therefore the ones that we should be targeting. So we've already started testing the pipeline. We've blindly redetected 4 known binary pulsars, which I've listed here, and their detection plots are on the right. So one of these is the double pulsar, which I managed to detect just today by running the pipeline, and that's on a observation which is about 14% of its orbit. So now that we've been able to, I guess, test an early version of the pipeline, we're sort of moving towards being able to actually apply this pipeline to actual Fermi candidates. And I guess I'll leave it there. So we've been able to detect 31 MSPs so far in the census, and our next steps will be doing this targeted search. And the publication for the MSP census is currently in prep. I'm happy to take questions.
Thanks, Garvin. Let's start with questions. I'll just hand the mic.
You mentioned doing searches based on largely on the galactic plane and on gamma ray sources. Are you also doing selections based on globular clusters?
So I think people have tried to observe globular cluster pulsars with the MWA in the past. So that is something that has been sort of looked into. I think there's maybe only been like 1 or 2 detections in globular clusters. They're mainly not really the types of pulsars that we sort of have the advantage to search for at low frequencies because when you're searching globular clusters, you need very long integration times to sort of be able to detect those pulsars. And also a lot of them have quite high DMs, which is not ideal when you're observing at low frequencies. So I guess it's a potential future avenue, but I think the Fermi sources is probably our best bet at the moment. At least while we're using the VCS system, because obviously very extremely long observations are not really feasible with the VCS system.
Any other questions? How about online? All right, let's give Christopher another round of applause.